Right, hello. In this video what I'm going to do is I'm going to talk about the three equations of motion. Now these are the three equations of motions that we can derive for constant acceleration, and we can also employ in many questions in order to get answers like what's the final velocity, the initial velocity, the distance traveled, or better still, the displacement of the body, the time it takes from reaching one velocity to the other, and different things. And we can even find the constant acceleration for those situations. So let me first state the equations of motion that we will be identifying, we will be deriving, and then we would go on to derive them in a very formal way. Now this way would involve calculus, it would involve integral calculus and differential calculus, and also would employ the concept of dot product of vectors. So if those three things are clear to you, it's wonderful there for you to watch this video completely and get a deep analysis and understanding of how can we get those rules in a very formal manner. Alright, to start it off, these are the equations of motion that we want to evaluate. So v at time t equals to v at time 0 plus a times t. V square equals v, this is v at time t, equals v at 0 square plus 2a dot s. And the third one is, well, s equals v of 0 times t plus half a t square. So here, let me write down what all the quantities that I have used here mean. So v is our well-known velocity. So this is the velocity vector of a body moving. V at some time is the velocity at that time. So this is velocity at time t. V of 0 hence would be when time is 0. That means the initial velocity that we start measuring. So say a body is moving along this trajectory with this as the x and the y-axis, then initially, say if we start measuring the body's motion from this position and we follow the body till this position, so this is the path traced by the body that we consider as a motion. Here at this point initially you would have a tangent to this trajectory which gives you, say, some velocity vector, and this is what we call v of 0. This is when we start measuring. After t amount of time that the body has traveled the green distance, the velocity changes to this new vector, and that is what I call v of time t. Now, it's always relative as to when we chose to measure the body. So this is the point where we start measuring it, a, and this is the point where we stop measuring it. So this is the motion that we're considering. Now, here, v of t has been explained, v of 0 has been explained. What about s and a? Well, a is your acceleration. So acceleration right there. Now this is an acceleration vector. It's very much like velocity. If you remember, velocity at time t was given by the derivative of the position vector of the body with time. In much the same manner as that, acceleration is given by the derivative of velocity vector at that time t. But in this case, things simplify very easily and to a considerable amount because acceleration is considered constant. So if something is constant, if acceleration is constant, if I were to take the derivative of acceleration with respect to time, I would have gotten an answer to be 0. So this is the constraint equation that we will be using in order to solve it, but that's for a later point of time. For now, let us clarify what v of t is, v is, what about a? Well, a is acceleration. What about s? Well, s is a very important quantity here. S is the displacement vector. Now, displacement is defined over a period of time, and as I've mentioned it before, we are actually measuring the body over the green distance. So displacement means that the displacement of the body from the initial position to the final position. And because displacement is independent and irrespective of the path that the body assumes, it basically joins the initial point, the final point, and hence the displacement vector is this blue straight line from A pointing to B, and that is what I call the S vector. So S vector could also be written in a very similar manner as r at time t minus r at time 0, because this is at time t equal to 0, and this is where the body would be at time t equal to t. So rather than writing r of t minus r of 0 every time, we try to write that as rt minus r0, and hence condense the use of the position vector and express everything in displacement vectors. It's much more easier to work with that. So there you have it. That is the displacement vector. And time, or t, is very well understood, and I hope it's very well known. That's just the time that we're using in order to measure it. Measure the motion and tabulate it. So there you have it. Those are the three equations. The most simplest one is the first one, and the other two can be used and can be evaluated just by the first one as well. So we'll go into those details now. So let me get rid of this for the moment and come back to the motion. So as always, we have our x and our y axis. They are very necessary because the body always moves along a trajectory, and the trajectory is understood only in terms of an x and a y coordinate system. So there you have it. So after 3 attempts, I finally gotten a trajectory that I'm happy to work with. This is a trajectory about which the body is moving, and as before, say we start measuring the motion of the body from this point, point A, and we stop measuring the motion of the body to point B. So to our understanding and to our knowledge, the body has moved from A to B directly, and therefore the following quantities are well known. This displacement vector, drawn in blue, originates at A and ends at B. You have position vectors as well. Position vector here, pointing from O, which is the origin, to A, that's the position vector at 0. From O to B, you get the position vector at time, well, say capital T, because here we're considering that the body goes from A to B at time t equal to 0 to time t equal to capital T. So the total motion happens over a period of time capital T. So the reason I'm doing that is because I want to use the variable t to measure a more general time. That is to say, that could be, say, when the body is at some intermediate position of, say, C, a point this. So we will try to use that definition of small t and that definition of capital T differently. So that is why I've chosen the motion to be constrained over the time interval of capital T, not small t. So there you have it, and those are the three other important quantities that we know. What about the initial velocity vector and the final velocity vector? Well, the final velocity vector is tangential to the trajectory, and that would be v of capital T. And initially, the body is moving somewhere there. So this is the velocity vector, and that would be v of 0. So there you have it. Those are all the quantities that one would need in order to go ahead. Now, let us come back to the most general and the most important statement that we have stated. That's the one that we started this video with. That statement was acceleration is constant. Now, if you go back to the definition of what acceleration is, and something that I've also covered in this video before, well, acceleration is the derivative of velocity vector. And what is velocity? Well, velocity is the derivative of position vector. So we can write it like so. Therefore, it's no surprise to write acceleration as the second derivative of position vector. So there you have it. That's another definition of acceleration. It's the second derivative of position vector. So if you think of r of t as a function, well, you take the second derivative with respect to time and you get a function of acceleration. And what we know about acceleration is this is independent of time. That means if you measure this at different time intervals, it gives you the same value. That's a key point to know at this stage. So what can we do with that? Well, let's use one of the equations. We know that acceleration is the first derivative of velocity, which is the same as saying it's the second derivative of position vector. So with this in hand, what we can do is we can integrate this with respect to time. In order to integrate the differential equation, we must multiply it by dt, the differential time element, and integrate it over a general time. So let's integrate it from 0 to time t. That is to say, we're integrating it from this point to at some time t, and we can always choose that time to represent capital T, or could also represent different points. It could represent point C with some other time interval that corresponds to the time interval between A and C. It could be a very general term. So we can use that, and that is what I'm integrating it to a general time t, not just a final time t. So same as here, we're integrating it from 0 to a general time t. So if you see this, well, on the right hand side you have a dt there, and you also have a dt there, which easily cancels out or basically gets eliminated. So you have the following. Well, you have a times dt, this is the vector, this is the scalar, and you integrate it from 0 to t. But what do we know about acceleration? Well, it is constant in time. So if something is a constant and you're integrating that quantity with respect to another quantity over which it does not vary, you can obviously take that out of the integral. That's what we're going to do next. We're going to take it out of the integral and evaluate just dt from 0 to a general time t. What about the right hand side? Well, the right hand side comes out to be the differential term of velocity, and that is it, and you're integrating it from 0 to t. So this gives you, and still this is just the right hand side, well, velocity at time t minus velocity at time 0. This is just as saying integral of dx from 0 to x is x minus 0. So it's the same as that, and basically this is how you expand it. So now you have the following. Well, a, which is this term here, and multiplied by the derivative integral of the derivative of t, which is basically t minus 0, equals to v of t minus v of 0. So this is no surprise, and it gives you the following. Let me change my color to this. Well, a times t equals v at some time t minus v of 0. So this is a more generalized equation of how velocity transforms, or how velocity changes. If we know the initial velocity vector at time t equal to 0, well, we can know the velocity vector at any random time. We can know it at c, we can know it at some other point, say d, or we can also know it at this final point b. What do we know about b? Well, for b, we know that the time that the body reaches b is after capital T amount of time when the body was at a. So the time is capital T. Therefore, v of capital T using this equation here gives you, well, v of 0, because this is a constant, plus a times capital T. And this is your first equation that we had written before. There you go, that's your first equation. So the velocity at final point B happens to be the velocity at initial point A plus the acceleration vector times time. And this is a very simplified version of how acceleration is, or what acceleration is. It's the difference in velocities divided by time. So from this equation here, acceleration does seem to be velocity difference divided by time, and that also holds. So there you have it, that's the equation 1, the first equation. So with that in mind, what we can do is we can work with different equations as well. So let's get rid of this for the moment, and with this understanding, it's very easy to go on to other aspects of this motion as well. So let's write our equation here. The first equation that we ended up finding was v of arbitrary time t is v of 0 plus a times that time t. So this is a more general way of stating the first equation that I had. At arbitrary time t, we can obviously choose arbitrary time t, small t, to be capital T in order to get our final equation. But let's work with this for the moment. Now, what do we know about velocity at time t? Well, velocity at time t happens to be the derivative of the position vector at that time t. Now, using this equation, we can use this statement and use it here. So this gives us, from this equation here, that the derivative position vector is nothing but the velocity at time t equal to 0 plus the product of acceleration times time. That is your new equation that we would choose to work with. What do we do with this differential equation? Simple as that. We integrate it with respect to time, 0 to t again, and we have to multiply it by a differential element there. So again, this term gets multiplied by dt, this term as well gets multiplied by dt. When you have a dt in the denominator, a dt in the numerator cancels it out, and you're left with 0 to t, integral from 0 to t, dr of t, that's it, equals, well, v of 0, integral from 0 to t, dt, plus a, integral t dt, 0 to t. And it's simple to see that I've taken out v of 0 and a outside the integrals because they are independent of time. V of time t equal to 0 is a constant. It's obviously known. It does not change with time. It's a known velocity at which we start measuring our motion with. Acceleration, by a condition, is also a constant, and hence both of them can be taken out of the integral sign. What are we left with eventually? Well, let's go term by term. The first term is just the integral of the differential element of position vector. So there is no surprise that this would just be r of t minus r of 0. It's just this term here evaluated at the upper limit minus the lower limit. It was the same thing as what we did previously. What about this term? Well, this term is v of 0 times same thing as what we had here. Evaluate t at time t and at 0 and subtract them. So t minus 0 is what you get. What about this term? Well, this term is a times, oh, but you have t dt. The integral of t dt turns out to be t squared by 2. And that's easy to see because if you take the derivative of this, you get 2t by 2, or that's t, and hence the integrand of t there. So that makes sense. The derivative of t squared by 2 is t, or the integral of t is t squared by 2. Therefore, this gives you t squared by 2 minus 0 squared by 2. How did I get that? I simply use the limits. Because this is not a general integration, but this is definite integration. It's not indefinite, it is definite. So we have not many zero terms which we can really cancel out because they really add nothing to the equation. So what we are left with is r of t minus r of 0 happens to be v of 0 multiplied by time t, a multiplied by t squared by 2. It seems like a complicated equation because it does not involve a displacement vector s, but it involves something more special, r of t minus 0. But what is r of small t minus 0? Well, we know r of capital T minus r of 0 is for sure the displacement vector across the entire motion that we consider. But r of t minus r of 0 is an even more general displacement vector, not the capital S vector that we are using. So what can we do with that? Well, we can certainly take time t equal to capital T, and if we change that, we get r of capital T minus r of 0, which is nothing but the capital S vector or the displacement vector. That comes out to be v of 0 times capital T plus the acceleration by 2 capital T squared. And there you have it. That's the second equation. So like always, we are defining a displacement vector as the vector joining the initial and the final point. But the initial and the final point differ by the time of capital T. If we were defining the displacement vector as a function of time, say between point A and some point C, this could be written as small s as a function of small t. And that would have yielded us a more general statement. The displacement vector across time small t happens to be velocity vector at time 0 multiplied by time t plus a by 2 t squared. So this is a more generalized statement of what I've written here. If you just change t for capital T, you get what we were looking for. But we are not done. We're not quite done now. Because at this point, we still need to evaluate the third equation. And to do that, we need to do something special. Alright, so how do you get the last equation? Well, the last equation is actually a scalar equation. These two equations, the first two equations of motion, are vectors because you see, you get a vector on the left-hand side and vectors on the right-hand side. They're all vectors. But the last equation was something to do with v squared equals v of 0 squared plus 2a dot s. And what about that? What do we do with that? Because this is scalar. All of these are scalar. This is dot product, which is a scalar. V squared is a scalar, and so is v. This is v at time t. So in order to do that, we need to convert one of these equations into scalars and try to see if this holds. So let us take the first equation that we know. First equation is v at time t equals v of 0 plus a times t. What can we do with this equation? Well, we can certainly dot it with itself. So we dot it with the v of t on the left-hand side, and we dot it with v of 0 plus a times t on the right-hand side. And the reason we can do that is because we are dotting it with the same quantity. Why are they the same quantity? Because v of t, as by here, equals v of 0 plus a dot t. So it's as though we're dotting it by the same. So this converts a vector equation into a scalar one. And let's see what this yields. This yields, well, on the left-hand side it yields v of t dot v of t. So that is the modulus square, or more simply, v of t squared. This is the absolute velocity at time t, an arbitrary time t. What about the right-hand side? Well, the right-hand side means, in order to evaluate the right-hand side, we need to evaluate term by term what happens to the dot products of individual terms with every other term. So the first combination would be v of 0 dotted with v of 0, which, like the same way we got v of t squared, we would be getting v of 0 squared. This is the absolute velocity square at time 0. What about the second term? Well, we multiply this with this. more specifically, we take the dot product of this with this, and that gives us v of 0 dot a scalar multiplied by t. What about the next term? Well, the next term is this dotted with this, which very much like the previous term is the same. So this is like v of 0 dot a times t. Remember, a dot v is the same as v dot a because that's a scalar term, and so it doesn't really matter how we write it. What about the last term? Well, the last term is a dotted with a, so that's a square. Again, we're only measuring the magnitude because it's dotted with itself. What about t? Well, the t multiplies with itself to give you t squared. There's no harm in that. What we can do now is we can see the similarities. Since these two terms are the same, it's better to cancel one out and write it as 2 times the other term. It's the same thing. So we have v at time t square equals v at 0 square plus a square t square plus 2v at time 0 dotted with a multiplied by t. Well, this seems unnecessarily complicated. What can we do with that? Oh, well, we see here that our equation that we intended to evaluate contains the term s, but it does not contain the term t. So it's obvious that we need to eliminate t from this equation in order to get this equation. How can we do that? Well, let's see what a dot s is. So from this equation, let me change my color. If I take this equation and I dot it with a on both sides, I get a dotted with s of t, which happens to be a dotted with v of 0 times t, plus a dotted with a, which is a square by 2, and that gives you t square. So you have an equation for a dot s, which is a dot v of 0 times time plus a square t square by 2. What can we do with that? Well, we see we have the same term here as we do here. So let us try to substitute this term in terms of s and t. We get v of t square, again this is the scalar term, v of 0 square plus a square t square plus 2, and what comes in the bracket is the following. The value of a dot v of 0 times t, or v dot a multiplied by time t. So that comes out to be a dot sf times t minus a square by 2 t square. I basically subtracted a square t square by 2 from both the sides to make this term the subject, and I got this expression for this term in the circle. What can we do with that? Well, we can multiply the 2 inside. This gives you 2 times this term, and 2 times this cancels out, and you're left with minus a square t square, and there is no use of the brackets anymore. So you have this equation finally to deal with, but wait, we have a square t square in the positive, we also have a square t square in the negative, and as simple as that may sound, you simply need to cancel these out because they're the same thing. A square t square minus a square t square. What are we left with though? Well, we are left with, well, v at time t modulus square, or simply the magnitude square of the final velocity, equals initial velocity square plus 2 from here a dot s. There you have it. That is the third equation. That's the third and the final equation. So these were your 3 equations that help you deal with motion in a plane, motion in constant acceleration, and this is how we make sense of them. So the reason we derive this by using very simple and very formal rules of dot products right there, calculus, integral, and differential, is to help you understand that all of those equations came out from just the condition that a is constant. A is constant, and hence the second derivative of position vector or the first derivative of velocity is constant. And just based on that, we were able to evaluate this, this, and this. So there you have it. Those are your 3 equations of motions that would do wonders if you understand them and would really help you to solve many, many questions, and also give you a very deep understanding of what is really going on and how the velocities change. So I hope this video made sense to you, and I hope it helps you in understanding the fundamentals of how these equations came about. So all the best and have fun.